Okay, so the first thing I would like to discuss briefly is what are the mechanisms of mode locking? How can you operate a laser, a multi-mode laser, in such a way that the modes tend to lock to each other, to prefer to beat in unison with each other, to reach their maximum at the same time. In fact, the equations are it's a rather difficult problem. These are non-linear equations. By non-linear, I mean that all the modes feed on the same medium. They extract energy from the same medium, so they compete with each other. And in this competition, many things can happen. Either one mode will kill all the others, and then it will be a monochromatic laser, or the modes will prefer to cooperate in order to extract the energy from the medium at the same time. And this cooperation between the modes is what leads to mode blocking. And there are several ways mode blocking can be achieved. One category is called active mode blocking. You do something, you apply a perturbation to the system which has a well-defined frequency. And if you do it properly, it will contribute to lock the modes. So I try to give you a qualitative explanation. Consider you have a few modes which are equally or nearly equally spaced, and you take one of the modes and you modulate its frequency. What you do is that you insert in the medium what is called a modulator, a frequency modulator, which is an electronic device which modulates the refractive index, which makes the refractive index vary in a sinusoidal way. This means that the frequency of one mode will acquire sidebands. And you will have not only the frequency nu, but nu plus or minus the frequency of the modulation. And if you adjust the modulation to be exactly or nearly equal to the spacing between modes, you see that the medium will be acted upon a frequency sideband which will coincide with the next mode or nearly coincide with the next mode. And then the two modes will have a tendency to lock together. And this effect was in fact observed for the first time, not in optics, but in mechanics by Huygens again. This happened, the story says that Huygens was sick and he was in bed, and in front of his bed there were two clocks, two pendulum clocks, which were hooked on the same wall. And the clocks, in fact, they were oscillating independently. And he saw that, he remarked, and that after some time, they started to oscillate together. So in fact, if you have two independent oscillators, which are nearly very close in frequency, and if they are coupled through the vibration of the wall, they tend to oscillate together. So this is the mode blocking of pendulums. In fact, there is a letter that Huygens wrote to his father in which he told him that he said, I just remarked that the two clocks are synchronized, oscillating together. Here, in the case of optical oscillation, it's one mode with its sideband. The sideband of the mode has almost the same frequency as the next mode, and so they start to oscillate together, and so they synchronize. But since you have a lot of modes, they all will go in sync together at with a very well fixed frequency difference. And this is active mode blocking. You can do that by modulating the response of the medium, by modulating the index at the frequency close to the spacing between the modes. Another way to look at that is to say the following. When you do this kind of modulation, it is as if you opened a window which has the same period as the time it takes for the light to go back and forth through the mirror. So then it's quite clear that if the modes cooperate, they will all pass through this window and not be absorbed. In fact, it's as if you open the gate which allowed a pulse of light to go through back and forth without being absorbed. So if you modulate the absorption with the right rate, you force the oscillators to cooperate in order to pass through this time modulated transparent medium at a well-defined time. So this is active mode locking. But there is another form of mode locking which is even simpler, which is called passive mode locking. And then it is based simply upon the fact that if you put inside the cavity a saturable absorber, so put something which absorbs, just of course it has to absorb a little bit, and by saturable I mean that this absorption is important if the intensity is weak, but proportionally it absorbs less at high intensity because of saturation, as we have already discussed. So if you put a saturable absorber, it means that if the intensity of the light fluctuates, which happens if the modes are not locked, the peaks of intensity will be favored. The peaks of intensity will go through more with less absorption than if they are not locked together. And so again, this mechanism of competition and cooperation between modes will favor the modes, will help the modes to cooperate and to be in phase together, because then they will be less absorbed than if they are not cooperating. And one way to achieve that is called KLM, Kerr length mode locking. What is the Kerr effect is just the fact that the refractive index depends on intensity. So if you put in the medium a slab of matter which has an index depending on intensity, it means that the index will be different in the middle and will decrease on the side because the intensity of the light decreases on the side. And so this medium will act as a lens which will focus the light. And if you put behind a diaphragm like that, you see that the high intensity light, which is more focused, will go through the diaphragm with less attenuation than the low intensity which will be spread on the edge of the diaphragm. So this kind of geometric structure, you put a Kerr medium, a nonlinear medium, and you have a well-adjusted diaphragm behind, it will favor intense light, which will be less absorbed than weak light. And so the different modes will have a tendency to lock in phase so that they can go through this medium with less absorption. And this is a passive mechanism of mode locking for lasers. But when you do that, it's not enough to get the frequency comb. But when you do that, you can lock together maybe a few hundred or a few thousand modes, and they are separated by the frequency of the oscillation, which is a few gigahertz. So you get a bandwidth which is a few hundreds gigahertz, which has nothing to do with an octave in optical frequencies. So to go further, you have to build what is called a white light frequency comb. And the principle of that is to send, you see, if you have only a few thousand modes, you see that each pulse will have hundreds of oscillation in it because it will be less compact than if you have a huge number of modes. And what happens if you go into a nonlinear medium? What will happen is that the front of the pulse will increase the index because of the nonlinearity of the medium. And so as the pulse is entering into the medium, the index will change as a function of time, which means that the wavelengths will expand. If n increases, lambda will increase too. And so you see that it amounts to modulating, it amounts to spreading the frequency of the medium. You see the edge of the pulse will, the electromagnetic field will oscillate faster at the front and in the back, just because when the light pulse enters into the medium, it changes its index as a function of time. And so you spread the spectrum of the pulse. And you get, for example, if you send a blue pulse, it will have an edge which will start to be red on the other side. And now you expand the frequency range over a wide band. And so I show you here how it works. What you have to do is to send your light, which is initially blue light, into a long fiber. So the light is guided in the optical fiber. And the optical fiber provides this nonlinearity. And in fact, if you want to have a strong nonlinearity, you have to structure your fiber in this way. This is a section of the fiber. And you see that the section of the fiber has the structure of a beehive. You have small holes which are organized like that. This kind of structure has huge nonlinearities. And you know, how do you build these fibers? It's very easy. You take capillary tubes, which have a large section. You put a bunch, you just gather a bunch of tubes like that. And then you heat with a torch and you stretch. You stretch. So if you take this kind of the bunch of tube and you stretch them, of course the volume is conserved, so you increase the length, so you decrease the surface, the section, and you get very narrow tubes which are bunched together, which have a section of a few a micron or less, and you get this kind of nano or micro fibers. The light which propagates in this fiber is strongly spread in frequencies, and you see if you put the extremity of the fiber into a prism, you see white light. It's a laser which has been spread of frequency from the blue to the red, and you have an octave in frequency difference. So when you take the spectrum of this, you get, it's like the spectrum of the sun, but of course, if you increase the resolution, it's not continuous. You have a frequency comb. You get equally spaced frequencies over a huge range of frequencies from the blue to the red. And this is the frequency comb. And these combs are very stable in frequency. You can control FR and F0, and you can use them as a real ruler to measure optical frequencies. So I just briefly indicate here how can you control, how can you measure FR and F0. FR is rather easy. What you have to do is to put a photodiode, a detector of light, and look at the bit note between two adjacent modes. And the bit note will give you FR. So this is just a beating between two modes. How can you get F0? The trick is the following. Take one peak of the comb here, which has a frequency KFR plus F0. You don't know F0, you don't know FR. And you send this light into a doubler of frequency doubler, second harmonic generation. You get 2 KFR plus 2 F0. And then you compare it with the comb, the peak here, which is a 2K case peak. The peak which has the order 2K has a frequency 2K FR plus F0. And so you see that this peak and that peak have a difference which is precisely F0. If you take one peak at one edge of the spectrum, you multiply its frequency by 2, and you compare it to the symmetric peak at the other side, you get exactly in the bit note, you get F0. So you need a second harmonic generator, just a crystal, which generates second harmonic, and you compare the frequency of the second harmonic with the frequency of the peak, which has 2K instead of K. And you can count all these peaks because the comb is stable. And so at the bottom of the slide, I show you how it works. You have here the frequency comb laser. You have here a beam splitter. You send part of the light into a photodiode and it just measures a bit note between two adjacent modes. That is what in fact what you measure here is the repetition rate of the pulses. And this repetition rate is compared to a cesium clock. And you decide you want to fix this frequency to a given value. So you lock your frequency comb to a given FR, which is measured by the atomic clock. Okay, once you have done that, you still have to fix F0. So how do you fix F0? Through this beam splitter, the second you have light going here, you send this light through the micro structured fiber. So this is a fiber which will give you all the harmonics, all the frequencies of the comb. And you arrive here, and here part of the light is going out. This is your signal, the output signal, and part of the light is going into a Mach-Zehnder interferometer. So this is the device which will compare the second harmonic with the the peak of the comb corresponding to 2K. So what do you have here? Here you have a dichroic beam splitter. That is a beam splitter which reflects this in this direction, which reflects the K harmonic, and it lets go the 2K harmonic here. So it's a beam splitter which has a different reflectivity for the frequency K and 2K. It lets 2K go straight and it reflects K down. And here you have a second harmonic generation. So here at this output port, you compare the peak 2K with the peak K multiplied by 2. And the difference gives you F0. So it's a Mach Zehnder which detects the bit node between the 2K harmonic and the 2K peak and the harmonic of the K peak. And you get F0 here on this counter. F0 is referred to the clock. And then what you have, you play, for instance, an intensity of the laser to fix F0 to a multiple of FR, which was fixed by fixing the length. So you see, you have two parameters you can play on to fix FR and F0 independently. And now you have FR and F0, which are both locked to the microwave clock, which is the standard of time up to now. So what do you do next if you want to do spectroscopy? Shown here, for example, the hydrogen experiment that I showed you at the beginning. How is the frequency measured? You have a very stable laser, and I will tell you in a moment how we get very stable lasers. You divide the laser into two arms. One arm is sent on the atomic sample to measure the frequency of the atomic transition. So you lock the laser to the atomic transition to be at the peak of the atomic transition line, for example, a 2-photon transition. And then the second arm is sent on the frequency comb laser. And you look at the bit node between this arm and one of the well-defined peaks of this frequency comb. And this is directly measuring, since you know which harmonic you are comparing to, you get directly the frequency of your transition measured by the cesium clock. So you see that you can use this frequency comb as something which multiplies frequency up to the optical, take a cesium clock frequency, multiplies it to the optical domain because of this formula, and compare it to the frequencies that you want to measure. And this is the way Hensch and his colleague measured with the precision that I indicated to you the spectrum of hydrogen. But now you can reverse the problem, because you will see that these optical clocks are much more precise than the microwave clock, because they count higher frequencies. So the ultimate goal is to get rid of the microwave standard and to use this clock as a new standard of time. So how would you do that? You start with this laser, frequency comb laser. You have this kind of spectrum. The first thing you do is to you bit two modes together and you send the signal and you fix the length of your cavity. So you get FR. Then you do also, excuse me, you get the beating between two modes here, you get FR. Then you take one mode here and the second harmonic mode, you beat them together as I showed before, and you get F0. And F0 and FR are stabilized, obtained here. So what you have here, you have a laser which gives you independently the frequency FR and F0. You manage to have F0 to be a multiple of FR. And so you see that at the output of this beating, you get something which is the atomic frequency divided by P plus Q. So you get a frequency which is now a divider of the atomic frequency. And the atomic frequency is here you interrogate your atom with a very narrow band laser, and you compare this laser to one peak of your frequency comb. So now the frequency comb is locked on an atomic transition. You don't have a microwave clock anymore. So your frequency comb is locked to an atomic transition, and you know exactly what is the divider of the atomic transitions that you have in each of your peak. So you have now a standard of time, which is whose divider give you a time locked on an optical transition. And what do you have here? Of course, here you need to have a very good optical transition. You need to have a very narrow transition, which can be either a trapped ion or an ensemble of cold atoms. And there are two kinds of optical clocks. There are the clocks which are locked on an ion, a single ion in a trap, and you have clocks which are locked on an ensemble of neutron atoms in traps. And I will discuss these two kind of clocks now. What I want also to stress is that this kind of laser, frequency comb laser, it's a laser in which pulse of lights are going back and forth between the mirrors. And this is exactly the kind of clock that Einstein imagined in his thought experiments. You remember when he described the dilation of time and the special relativity. I use this kind of clocks. Einstein, in fact, used this kind of clocks, pulse of light going back and forth between mirrors. And it's exactly what we do now. With lasers, one is able to realize the kind of virtual atomic clocks that Einstein imagined in the thought experiments of the beginning of the 19th century. So, first of all, how can you, what kind of experiment can you do with a single ion? This is a mercury, the first optical clock was a mercury ion clock. So you see, this picture shows a single mercury ion here. This bright spot is just one ion of mercury in a trap, which is illuminated by this UV laser beam at 194 nanometer wavelengths. So the transition, the energy level scheme is shown here. You have here the transition at 194 nanometer, which is strongly allowed. So the atom is going back and forth, absorbing and emitting fluorescing light. This transition is used for detection. It detects the bright spot, shows that the atom is in the ground state here. And here I have a weakly allowed transition going to a level which has a very long lifetime. This transition is very narrow because the lifetime of the excited state is long. And a very stable laser is interrogating the ion on this transition. And you see that as soon as the laser will bring the atom from this state to that state, this will extinguish the fluorescence on the other transition. So this is a technique of quantum jump spectroscopy that I discussed a few weeks ago. What you do is that you sweep the frequency of this laser and you look at the frequency of the quantum jumps. If you are on resonance, you have a lot of quantum jumps. If you are away from resonance, of course, the system stays alight all the time, you have no jumps. And so this is quantum jump spectroscopy, which allow you to find out where is the center of the resonance. And of course, then you compare it with a frequency comb. You compare it at that time with the frequency standard, because we are still in the building process of these clocks. And so this was the first mercury clock. I show you some figure here. The frequency is about 1.06 10 to the 15 hertz. And the relative uncertainty is 7 10 minus 15 per square root of second. And it means that you reach an uncertainty which is 10 minus 14 per second, which means that it's about 10 minus 16 per day. So you have now something which is better than the cesium clock by the same order as the fountain clock in the microwave domain. So this was the first one, but a lot of progress has been made with this aluminum clock. And I would like to spend a few minutes on the aluminum clock because it's a clock which uses a quantum gate. In fact, what I want to say is that when the experiment was done in Boulder by Dave Wineland and his colleagues, and they found out that aluminum has a very good transition. You see here, the transition at this frequency here, 2.67 nanometer, it's a UV transition. It has a very long lifetime in the excited state, so it's a very good clock transition. But the drawback is that there is no convenient transition for the cooling and the detection. There is not a good transition for looking at the fluorescence and using a transition to cool the aluminum ion. So the technique that Wineland and colleague used is a very clever one. They put another ion in the trap. So you have the aluminum ion, and you have either a beryllium or a magnesium ion, which is used as a detector for the aluminum ion. In fact, the two ions are together in the trap, and the beryllium ion, and we look at this case, as you will see in a moment, the beryllium ion has a good transition for cooling and detection. You see here the energy levels of beryllium. You have two ground states, F equal 2 and F equals 3. No, F equal 2 and F equal 1, two ground state, and they are connected by a Raman transition. So it's a qubit between two ground states. You have a Raman transition that connects one to the other. And if you remind yourself of what I discussed the other day, what you can do is to change the vibration quantum number by exciting this Raman transition on a sideband. So instead of having omega 1 minus omega 2 equal to the qubit transition, you have a sideband you excite with omega 1 minus omega 2 equal to this plus or minus omega r, which is the vibration frequency. And so the two ions, aluminum and beryllium, are coupled through the Coulomb interaction. They share a common mode of vibration. So you can excite, and this is the principle of the quantum gates with ions, you can excite on one ion, you use one ion to excite a vibration mode, and then you transfer this vibration to the other ion. So you have to process by sequence of pulses, a first pulse on the first ion, which creates this vibration, and then a pulse on the second ion, which takes this vibration and put it on the qubit state of the second ion. And I will show you how it works here. You see that we are using here this transition, which is shown by this red curve here, is the clock transition. And here this is a transition which excites, you take a blue sideband excitation, and you make a pi pulse, which bring you from this ground state to this excited state plus one vibration quantum. So you see that you copy the clock qubit, this state 1s0, you copy it on a vibration quantum. You start from 1s0, 0 vibration quantum, and you go to the excited state plus and 1 vibration quantum. And the second ion, which has been prepared in F equal 2, stays there because it is not excited. So you see this is just a pi pulse on the blue sideband, which creates 1 vibration quantum for the ensemble of the two ions. And then the next step is to apply a pulse to the second one, and you apply now a pi Raman pulse, which will take this n equal 1 vibration quantum and bring the system back to n equals 0, but this time it will act on the qubit of the second ion, F equal 2 to F equal 1. So what you have done with these two pulses is to carry the excitation from 1s0 to F equal 1. You are in F equal 2 and you are finished in F equal 1. And now F equal 1 is a state which, F equal 1 is the state which has been reached here, but you see that the F equal 2 state is a state which is scattering photons very strongly on the beryllium ion. So this is a detection. Detection is obtained by this transition. And you see that for this transition to occur, the atom has to be in the F equal 2 state. So what happens now? Look at what happens. If the atom was at the beginning in 1s0, that is in the ground state of the aluminum ion, you see that the beryllium is not fluorescing because the beryllium has gone from F equal 2 to F equal 1. And so the beryllium does not fluoresce if the aluminum ion is in 1s0. On the other hand, if the aluminum ion has been transferred to this state, he is no longer here. And so in this case, the beryllium stays in the fluorescing state here. And you see that you have fluorescence. So you see that the fluorescence of the beryllium ion depends upon the state where the aluminum ion is. If the aluminum ion is in 1s0, there is no fluorescence. And if the aluminum ion has gone to the excited state of the clock transition, the beryllium ion is fluorescing. So you have here a quantum gate which allows you to detect the transition in aluminum via what happens on beryllium, because the two ions talk to each other through the Coulomb interaction, which makes them share the same vibration mode. So this is what has been observed. And you see what you have to do is to apply a sequence of pulses. You have to initialize the system so that the beryllium ion starts in F equal 2 and the aluminum ion in 1s0. And what you do is that you apply the probe laser on the clock transition for a given time. And then you ask the question, is the aluminum in 1s0 or in the upper state of the clock transition? And to do that, I apply the sequence of sideband transition to transfer on the beryllium, and I look at the beryllium fluorescence. And then I start again. And what I do is that I change slowly the frequency of the probe laser, and I look at what happens. And you see here what is observed. First of all, here you have an histogram which shows what you expect when the atom is in the 1s0 state. You expect not to see fluorescence. So you see that you have 0 fluorescence photons. And that's it. On the other hand, if the atom is in the if the aluminum atom is in this state, then you see a lot of fluorescence in beryllium. On average, you have about 10 photons per cycle during the time you look at the fluorescence. And you see here, it's just a Rabi oscillation. You see the probability to be in the P state as a function of the duration of the interrogating pulse. So you shine light on the clock transition. And as you wait, you see, of course, the Rabi oscillation. The system oscillates from 1s0 to P0. When it is in P, you have a lot of fluorescence from beryllium. When it is in S, you have no fluorescence. So you have a modulation of the fluorescence rate. So it means that this communication between the aluminum and beryllium works. And then what you do is to do again the experiment, but this time you fix the time to have just a pi pulse, a pi Rabi pulse at resonance. And then you scan slowly. What you do is that you scan the frequency of the laser and you get what I call Rabi spectroscopy. You get the probability to excite the atom as a function of the frequency, and you get the sign, this usual signal, and you lock your system at the center here, and you use the frequency comb to count the frequency and so on. So you see that this aluminum beryllium clock works well. It allowed to measure the frequency of aluminum. You see you have something like 15 or 16 digits. And the error you have here is not due to this clock. This error comes from the microwave clock. The fact that you count a frequency with a clock which has a precision of 10⁻16, it's a fountain cesium clock. So you see the huge precision that you get. And if you want to see the real uncertainty, what you have to do is to build two clocks and to compare them, because you cannot compare them with a microwave clock, which is not as good. And the beating between two optical clocks is what I show you on the next slides. But at first, I have to tell you a little bit about two devices which are very useful in these experiments. You know, the principle is the following. You need to have a very stable laser. The laser which is interrogating your clock transition has to be very stable, has to be a very long coherence time, a very narrow spectral width. And to get this laser, you stabilize, in fact, a laser on a very, very good cavity, a passive cavity, a cavity which is made of a single block of silicium. It's a kind of solid cavity, which is insensitive, widely insensitive to vibration, insensitive to thermal expansions. I will show you this kind of cavity in the next slide. But once you have your laser stabilized like that, you don't want to touch your laser anymore. So how do you scan the frequency? To scan the frequency, you use this is called an acousto-optic modulator. It's a quartz, it's a piece of glass or quartz in which you induce a vibration which propagates. It's a kind of sound vibration. It's a source of sound wave which propagates along this medium, and these sound waves makes successive planes on which the light is scattered, and you get a kind of Bragg scattering. There is an angle for which you have a positive interference, and this light is scattered on a wave on a grating which is moving, of course, because it moves like a sound wave. So you have a Doppler effect, and in fact, the light which is reflected in this direction is a sideband of the laser. It's nu L plus nu sound. And so this acousto-optic modulator is a device which allows you to shift the frequency, well-defined frequency of a laser. And when you change the frequency of the sound wave, you just scan the frequency of your laser. So the advantage of this is that you don't touch your laser. It's very stable, it doesn't move, but you are able to get a different frequency by mixing the frequency of the laser by the frequency of the sound wave through the acousto-optic modulator. And now to stabilize your laser, you use what I showed you. This is a picture of these cavities. You have two mirrors at the end. The cavity is a solid block of silicium. It works at a temperature for which the expansion of is zero. There is a magic temperature for which you have no expansion of the device. It is suspended by a very thin quartz wire in order to avoid the vibration of the ground. It has to be under vacuum. It's a very stable cavity. And you see the kind of scan when you scan your laser across the resonance of this cavity, you get a very, very narrow peak, which is only, you see here, only 34 millihertz in width. And you see a very, very narrow. We are talking about frequencies in the range of 10 to the 15 hertz, and you have now something which is 10⁻16 of the Q of this transition is about 10 to the 16. So a very stable laser. And then you scan this laser with the acousto-optic modulator around its frequency. And you get what I show you. Next slide. Here, this is a device which compares two aluminum clocks. So you have one aluminum clock in which the companion ion is magnesium, and this one has beryllium. So you have two clocks which are different. One is using magnesium as a reader, and the other one is using the beryllium. The same principle. It transfers the excitation of one cubic state to the other by the process I described. You start with a very stable laser, which is stabilized on this cavity. And then you have acousto-optic modulators. And so you change the frequency to be in resonance with this clock. And you have another acousto-optic modulator, which brings you in resonance with the other clock. And when you compare the frequencies of these two acousto-optic modulators, you have the difference frequency between the two lasers. And you have frequency multipliers also, because you start with a laser which has a frequency which is half the frequency that you need for your transition. So this is a general principle. And from this comparison, you get to the conclusion that these clocks have an uncertainty of 10⁻17 per day. So it's a win of a factor of 10 over the best fountain clock. So at this point, you might ask, why only a factor of 10? The frequency is 4 orders or 5 orders of magnitude larger, and I win only a factor of 10. The answer is that on the cesium clock, you have 1 million atoms in your, when you lift the atom in the fountain, you interrogate 1 million atoms. Here you interrogate only 1 ion. So you lose a factor of 1,000 on signal to noise. So in fact, you win only a factor of 10 because the microwave clock is much better in terms of averaging atoms. So this brings me to the last point. If you want to do better, what you cannot do it with ions, because if you start to put more ions in the trap, they will perturb each other by the Coulomb interaction to become impossible. So what you have to do is to use neutral atoms in an optical lattice, and you put 1 atom per lattice side. So the atoms are very far from each other at a distance of the order of 1 micron, which is very big. They don't interact with each other. And then you can win this square root of n factor because you can start with 1,000, 10,000, 100,000 atoms. And these are the optical clocks with neutral atoms. So they are better than the ion clocks because you win in the signal to noise. And this will be the end. But before that, I show you a historical experiment with 2 aluminum. You take an aluminum clock and you move it, you put it on a table with a jack. You can just raise it in the gravitational field of the Earth. And this is an experiment which was done by the Weinman group in 2010. You see that the frequency of the clock varies. When you move it up, it goes faster. And this is a difference. This is a gravitational redshift over a difference of 30 centimeters. So this clock is able to show that the clock does not tick at the same rate here and there, at 30 centimeter difference, because of the gz over c squared term of general relativity. So let's go now to the neutral clocks. So this is what I said. You have to pack neutral atoms in traps, and there are several groups in the world which are doing that in the United States, in Germany, in France, in Japan. And the big progress in this field was achieved when Katori in Japan understood the big drawback, the big problem with optical clocks is that the atoms are trapped in an optical potential. And this optical potential, it's a light shift effect, it is not the same in the ground state and the excited state of the trap. When the atom moves from the ground state to the excited state of the trap, it sees a different light shift. And so the frequency of the atoms depends upon the intensity of the light. And this is not good at all. But Katori had the idea, found that there are some magic wavelengths for which the polarizabilities of the label are such that the light shift is the same for the ground state and the excited state in the trap. And if you use as trapping light, a light which has this magic frequency, then the frequency will become independent of the light intensity. And this will give you a good basis for a clock. So there are 2 kinds of ytterbium and strontium clocks. The structure is always the same. You have the clock transition here, which has a very long lifetime for the excited state. And this transition, which is used for cooling and detection. And you see the kind of traps that you have. The atoms are trapped in a kind of nest structure. It looks like an egg box in which you have 1 atom per side. And you see that if you are at the right frequency, you see that the ground state and the excited state see exactly the same potential. And so you have now an optical frequency which is independent of the intensity of the trap. And this is obtained, you see here at the bottom, you see here the polarizability of the levels. You have resonances, and you see here, you have this magic wavelengths for which the polarizability of one level crosses the polarizability of the other. And this is a kind of wavelength which is chosen for ytterbium and strontium. Again, you have taken two clocks of this kind. So you have here the optical lattice, which is performed with 3 beams in all directions. This is a second laser and the second clock. So you have one ytterbium clock here, one ytterbium clock here. You have just one master laser here, which is locked on this very stable cavity. And this laser is the laser light goes to one acousto-optic modulator here, to another acousto-optic modulator here, and they are locked. This is a fluorescence light which is detected from the ytterbium clouds, and all this is used to lock the system. And you compare the frequencies of the two ytterbium clock as a function of time. And you see that you average over longer and longer time. The uncertainty decreases as square root of tau. So this is just a diagram which shows the increase of sensitivity up to 10,000, 100,000 seconds. And now you have on this clock uncertainty over a day, which is 10⁻18. 10⁻18 is, I need to do the calculation, it's less than 1 second over the age of the universe, kind of stability and uncertainty that these clocks have. And with these clocks, and I am concluding here, you see that how the precision, the accuracy of atomic clocks, this line are the microwave clocks, and this line gives you the precision of the optical clocks. You see they crossed each other around 2000. They crossed each other over 2005, 2010. This was the status at this point. It was 10⁻18. Now, this point here is the last clock. It's a strontium clock by the GILA group, which has an uncertainty of 10⁻19, which is less than 1/20th of a second over the age of the universe. And this clock is symbolized here. So this is the cloud, the lattice of cold atoms, strontium atoms, and you see the number of digits with which you can define the frequency. Of course, it stops at 17 digits because for the time being, the only way to define the frequency is to compare to the microwave clock. But these 17 digits are 2 digits away from the ultimate precision that these clocks can have. And this clock has been used to measure the gravitational redshift for a difference of altitude of 1 millimeter. So it's 100 times more precise than the experiment which was done in 2010. I just gave you here the reference if you want to look at the paper. You have it has just been published last month. So it's a very, very new result. And so I come now to the conclusion. So time can now be measured with a precision such that 2 optical clocks do not deviate by more than a fraction of a second over the age of the universe. The definition of the second, which is still based today on the cesium microwave clock, will probably soon be redefined with improved precision as a multiple of the period of one of these ytterbium or strontium optical clock. And but of course, if you define the time standard with this clock, you will have to precise where you are in the gravitational field of the Earth, because this clock in Boulder, which is 1,600 meters high, it does not tick at the same rate if you are here in Rome or in Paris. So the problem is to define the time at a given altitude in a given gravitational field. Second, so what could be the use of these clocks? These clocks on ground or embarked in satellites will allow physicists to test with increased precision the special and general relativity theories. It has already started with what I just mentioned. There is also a very interesting test of cosmological theories, which says that the fundamental constant, the fine structure constant, or the ratio between the electron and the proton mass depend upon time, that they should evolve in time. And ytterbium, for example, ytterbium and strontium, the frequencies of ytterbium and strontium depend in different ways of the values of this constant. So if there is a change of alpha or a change of small n over electron mass over the proton mass over time, a cesium, a strontium and the ytterbium clock will deviate from each other and will not count the same time. And so there are experiments which are now done to try to test these cosmological theories. You can, at a more practical level, if you move this clock and if there is an inhomogeneity of masses underground, you will be able to see it. So it can be very useful for geophysical investigation to try to find if there is some interesting minerals in the ground. It could also, if you can think of observatories in which you would put 2 or 3 clocks at different points and be able to see by the different times they indicate whether there are motions inside the Earth, very small motions, which are precursors of earthquakes or volcano eruptions. So it might be possible to use these clocks as very sensitive probes of change of gravitational fields. There is also some thought to, if you can still increase the precision, go to 10⁻20 or 10⁻21, then the times that these clocks give would be sensitive to gravitational waves. So when a gravitational wave passes through the clock changes, the rhythm of the clock at in the given frequency interval in a given short time could change. And this would be an alternative to the gravitational wave antennas, which now use huge lasers over kilometer distances to measure these waves. So there are many, many possible applications of this thing. Now, just as a final note, I would like to come back to the general idea of this talk. If you want to get more and more precise clock, increase the frequency. So what is beyond optical frequency? Beyond optical frequencies, you have, of course, XUV or gamma rays. And gamma rays clock would be clock which will be locked on a transition between nuclear levels, not atomic energy levels, but levels of a nucleus. And so there are now some research in this direction. You have to identify nuclear transitions which have long lifetimes. And of course, you will have to construct the equivalent of a frequency comb, which would extend into the UV and the gamma rays. For the time being, we don't know how to do that, but maybe the next generation of very precise clock will measure time with this kind of transition. And then the definition of time will be changed. And the challenge, of course, is to be able to define a time which keeps a meaning in spite of the fact that it becomes so sensitive to gravitational fields, for example. So I will stop here and just tell you that the last 3 lectures will be devoted to one field that I have not discussed yet, which is more closely related to my own research. I will talk about cavity quantum electrodynamics. That is, I will discuss phenomena which occur when an atom has an environment, has a cavity around it, which change the density of mode of the field around it. And you will see that in this case, the properties of the atom can be changed, and you can have a system in which atoms and photons interact with each other in a way which is different from the one I discussed up to now. So this will be the topic of the final lectures. Thank you.